Hello everyone. In this video we are going to discuss another informed search algorithm called as A-star search algorithm. In the previous video we have seen greedy best first search, which is also an informed search algorithm. But we have seen that greedy best first search is not optimal and not complete. So in this video we are going to discuss an algorithm which is optimal and also complete. And we will also see what are the limitations and how it differs from the greedy best first search and also other algorithms which we have discussed in uninformed search algorithms. So just to give a brief picture of what we have seen earlier, in the uninformed search algorithms we have seen many types of algorithms like breadth first search, depth first search, iterative deepening, bidirectional search. All those are uninformed search algorithms where we did not have any extra information regarding the problem, whereas in the informed search algorithms we have extra information regarding the problem in the form of a heuristic function, and there we are including that heuristic function before we choose the nodes for expansion. So in the previous greedy best first search informed search algorithm, we have only used heuristic function as an evaluation function, whereas in A-star search algorithm we not only have heuristic function but we also have the path cost, which we call here as g of n. So let us see the more details of how this algorithm is developed. So A-star search algorithm is also a best first search algorithm. It evaluates nodes by combining g of n, which is a path cost from starting node to the node n, and we also have an h of n, which is the estimated cost from node n to the goal node in the cheapest path. So there are two components in the evaluation function. One is g of n, which is the cost incurred to reach to the node n, and h of n is the cost incurred, the estimated cost which might incur from node n to the goal node. So h of n is an estimate, it is not actually a deterministic or a fixed factual information. We try to use various heuristic functions, and we get an estimate of how much cost it would incur to reach to the goal node. So using these two functions we are going to calculate f of n, which is the summation of g of n and the h of n. So this f of n will be the estimated cost of the cheapest solution through n. So as we are passing through node n, so f of n at node n would be the summation of g of n and h of n. So but h of n should satisfy certain conditions. We will be seeing those conditions, what it needs to satisfy. But the important thing is A-star search algorithm is optimal and also complete, which means that we are going to definitely find an solution which means that it is complete, and not only that, the solution it gives is optimal, which means that there is no better solution than the solution what A-star algorithm gives. So A-star algorithm is identical to uniform cost search, except that A-star uses g plus h instead of g. So here we can make a comparison between how A-star uniform cost search and greedy best first search algorithm differs. So let us see that. So as we can see here, uniform cost search has f of n evaluation function is directly equal to g of n, whereas in the greedy best first search we don't have g of n, we only have heuristic function, which is an estimate of the cost from node n to the goal node, and we have A-star search algorithm which has both g of n and h of n. So this is how it differs, but the important thing to note is uniform cost search is a uninformed search algorithm where we did not have any estimate or any heuristic function and any domain specific knowledge, whereas greedy best first search and A-star uses a domain specific knowledge, and that's why we have a heuristic function h of n. So let us understand the A star search algorithm with an example. Consider this graph which contains 6 nodes. A is the starting node and F is the goal node which we would like to reach. The edges are the cost incurred to move from node A to node E. At each node we also have a heuristic function value, which is the cost incurred from particular node to the goal node. It's an estimate of how much cost incurred from the particular node to the goal node. So let us see how we can solve this problem. So now consider, let's represent this in the form of a tree. So consider the starting node A. So if you see the node A, we have B and E as the child nodes with cost as 0 and 10 respectively. So if you compute the f of n value for the node E and node B, we have estimate h of B as 100 and h of E as 0. So and g of the cost incurred to path B is 0 and cost incurred to path E is 10. So if you sum, we get f of E as 10 and f of B as 100. So as we can see here the node f of node E has a lesser cost, and therefore we are using here also a priority queue, just like how we have used priority queue in uniform cost search and also in the greedy best first search algorithm. So this priority queue will pop the node which has the least cost. So here the cost node E has the least cost, which is 10. So it is going to expand node E. Node E has only one child, which is the goal node F. But the important thing to note is it is not going to stop here once it sees the goal node. It is going to check all other paths to find out if there is any other better path to the goal node. So here as we can see in the frontier list, which is the open list which contain B node with 100 cost and F as 110. So the node B has now lesser cost as compared to node F. So we can pop the node B and expand it further. So B has only one child, which is C. So when you expand it, you will get f of C as 101. So f of C contains g of C plus h of C. G of C is 1 here, as we can see in the graph, and h of C is 100, which is also mentioned underneath the C node, so which sums up to 101. So now the node C is kept it in the reached nodes or closed list. C has only node D as the child node. Once again, in the frontier, the cost for D is 102 and cost for F is 110. Still the node E has lesser cost. So node D is popped and placed it in the closed list once again. And we can see now from node D to node F, the cost incurred, the path cost is 100. So now when you sum up all the cost from node A to node F through B, C, D, the cost incurred is only 102. So that is lower cost as compared to the cost passing through E. So 110 is replaced by 102. So in this way, just like how we have seen greedy best first search algorithm, it uses priority queue to pop the node which has the lowest cost, and also whenever it finds a better path with a lower cost, it will replace the frontier with the lower cost. So that's how A star search algorithm works. The only difference between A star and the greedy best first search is we are using both path cost g of n, which is the cost incurred to reach to the node n, and we have an estimate of the cost for moving from node n to the goal node. So both these put together, we try to pop the nodes based on the node which has the least cost. So this is how A star search algorithm works. So let us now see when you could get the optimality. We said that A star search algorithm is optimal and complete, but there are conditions, two conditions, which is admissibility and consistency. Admissibility says that our estimate at any particular node should not be overestimate to the cost to reach the goal, which means that if we know that, which means the cost it estimates to reach the goal is not higher than the lowest possible cost from the current point in the path. So if there is a path which has a particular cost, our estimate should not be more than the shortest, the current path which is available. It should not be an overestimate. It should not be higher than the already existing path. This is one of the condition for optimality, which is admissibility. The second is consistency. Once again, h of n should be less than or equal to c of n comma a comma n dash. So here n is the node n dash is the node n dash, or the succeeding node. A is the action taken on node n so that it moves to node n dash. C is the path cost between node n and n dash. So h of n should be less than or equal to c of n comma a comma n dash plus h of n dash. So as we can see here, we have node D and node E. The path cost is c of d comma a comma e, and node D, at node D we have the estimate as h of d, and node E we have the estimate as h of e. So h of d should be less than or equal to c of d comma a comma e plus h of e. So this is the condition, consistency, and if you see, the consistency implies admissibility, which means that every consistent heuristic is also admissible. So but not vice versa. So these two conditions are needed to say that A star algorithm is optimal. To say it complete, we have another condition. Completeness requires that there be finitely many nodes with cost less than or equal to C star. A condition that is true if all step costs exceed some finite epsilon, and that is usually we don't have path cost as negative, we don't have path cost, we need some finite value epsilon for path cost, and finitely many nodes with cost less than or equal to C star. If it is satisfied, then we can say that completeness, which means that we are going to definitely have the solution for the goal node, and we don't expand the nodes which has f of n greater than C star. If you remember, C star is the total cost which we have calculated in the uniform cost search. So in summary, A star is optimally efficient for any given consistent heuristic, and which means that no other optimal algorithm is guaranteed to expand fewer nodes than A star. So A star in terms of optimality is a perfect algorithm, search algorithm, but time complexity if A star is once again exponential, which is order of b power d, where d is the branching factor and d is the depth. Although it largely depends upon the chosen heuristic, because if you choose the heuristic, you can prune particular subtrees and thereby you can reduce the complexity. But one of the main limitation of A star is the space complexity. The space complexity, it almost stores all the nodes in the memory, and it is one of the biggest limitation of A star algorithm. So for the larger graphs, it becomes difficult to apply A star because of the memory requirements. But to overcome this, memory bounded heuristic search techniques like iterative deepening A star, memory bounded A star, and SMA star are developed. So some of these algorithms we'll be discussing in the next video.